First, I'd like to thank the organizers for inviting me to come and give a talk today. And especially I'd like to thank, because I'm a newcomer to this field, all of the speakers so far, and I'm sure there'll be more for the rest of the day, for giving me a crash course in this field. And it's been really very informative, and I've really enjoyed the talk, so thank you. So I'm going to talk about climate modeling. I'll talk a little bit about how we got where we are, and when you talk about climate modeling, of course I should say, but I always say climate modeling, but Earth's climate and present day climate is what I'm doing. So that's my focus. And so when you talk about that, you have to talk about the IPCC and those sort of activities. But in hearing the talks this week, I've thrown so much into this talk since during this week, because I'm like, oh, they might want to know about this. So I'm going to talk a little bit about the upper atmosphere modeling, which I think might actually be of interest to people looking at things like escape and that sort of thing. And then I'll talk about the future directions for climate modeling and how relevant that is in terms of planetary atmosphere modeling. Okay, so where do we begin? Well, back in the first real coupled climate model was by Manabe and Bryan in 1969. This is a GFD model, and we went from, this is their representation of land and sea and that sort of model. So you can see, but it wasn't long really. It just before we started talking about models that are actually not that far off the resolution of current models in terms of planetary atmospheres, and. But interesting, even back then, they started talking about these things about how to couple these different components into the system. And this is really what we still do today in terms of how we couple models together. So what happened since 1975 to present in terms of climate modeling? Because back here, they'd already coupled the ocean to atmosphere and a land model. So really, what happened is an explosion of complexity in the different components of the modeling system. So you started adding in sea ice models, and then they realized the importance of volcanic eruptions, and so they started adding in sulfate aerosols, and then they coupled into the carbon cycle to really understand the CO2 and nitrogen fluxes in the atmosphere. And then now, more recently, we've got active ice sheet components to understand how things, land ice varies with climate change. So these are dynamic ice models. And then also in the last decade or so, we've really started to expand the lid of the model to include the upper atmosphere, and added in interactive chemistry. And that's become more and more complex. And we're coupling into biogeochemistry in the ocean as well. This is sort of gives an idea about the timeline in terms of how these different parts were added in from the mid-70s all the way up to around 2014. These numbers, the words up here say FAR, SAR, TAR, AR4, AR5. That's the IPCC assessment reports. So the first assessment report, second assessment report, et cetera. And so these are the points at which people were sort of targeting model development, and then those papers that were describing the current research were then written up in these assessment reports that talk about the state of the climate. While these processes were being added to the model, of course, there's this inexorable march to higher resolution in the model, and so really the costs, the modeling, the computational costs of these models are I guess, kind of ramping up with the capability of the computer architecture. And I think we kind of have a benchmark that we need to be able to do about 5 years to 10 years per minimum per wall clock day in our simulations to have a viable climate model. So that kind of limits us in terms of, and really has pushed us to look at things like how we parallelize these codes and how we run on many, many processors. So what do we do with these climate models? Well, after we benchmark them on terms of reproducing the recent history, the last 150 years, we do these run these different scenarios for future climates. So these are typically described in terms of an RCP, or recommended climate protocol, or actually recommended concentration pathway. Sorry, and they are indicated by they're typically indicated by their forcing in watts per meter squared at the end of 2100 here. So for instance, RCP 8.5 has 8.5 watts per meter squared, which is roughly 1,370 parts per million of carbon dioxide. But this is about all that we are doing in terms of pushing our climate models to higher concentrations of carbon dioxide. And so this is something you have to bear in mind, that these models, what they are designed, the environment, the sort of regime they're designed to work in. And so these scenarios have attached to them different projections on the concentration of radioactive gases, and these are degraded in the model. So methane will then produce water vapor in the stratosphere and is an important greenhouse gas in itself. And the CFCs are also built in here. And then this is the sort of the results. This is now these numbers here. 39 is it says that there are 39 models here that ran that particular scenario, and probably some of them did many an ensemble of runs in order to understand the spread of the model and the spread of this prediction. And you can see that on average, these models are producing something like about under that scenario, a sort of 8 Kelvin warming. But that's in a global mean sense. When we look at these things, these are now different scenarios from, this is the 2.8, 4.5, 6.0 and 8.5 scenario. This is now looking at the period change in temperature from pre-industrial conditions. So we can see we have about a 1 Kelvin warming over a lot of the planet here, but it's statistically significant over a large portion. And then by the end of the century, we're going to be talking up to sort of 7 or 8 Kelvin, dependent on the region of the atmosphere. And what you notice in this figure is that you see polar amplification. That is, that while the atmosphere in general might have an average increase in temperature, you get more warming in the poles, and that's simply because you have melting of the ice caps, and so the albedo of the planet changes up there, and you get an enhanced warming at the poles. Okay, so that's not everything's about temperature. We can talk about precipitation changes in the model, and so you can see here this is a change in precipitation. Large regions of the atmosphere are drying here, especially sort of in Southern Europe. Some regions actually get wetter, and this is what we might expect, that if you have a warmer atmosphere, it's going to hold more moisture, and you may get stronger precipitation events in the tropics, say. So, and this could also come from things like how the circulation is accelerating, and that affects the distribution of water vapor. So that's sort of the IPCC scenario. One of the things that we do, though, and we're doing more now, is sort of asking how does the model respond to a particular forcing. So we did one of the canonical ways you look at a model is in terms of its climate sensitivity is by doing an instantaneous increase in carbon dioxide of what we call a 4 times CO2 experiment. So you have a model that runs is in equilibrium, and then all of a sudden, all you do is you change the carbon dioxide in the model, and that will introduce a sudden radiatively, the model will be in balance and will start to warm up. And so you see this temperature rise, and maybe after 150 years or so, it's starting to come into somewhat of an equilibrium into that new climate. You can plot this delta T versus the top of the atmosphere radiative imbalance here, or N, and you fit that to a line. And if you follow this, extend this line down, you can say that this is probably where the model is going to end up in terms of its new equilibrium temperature. Where it started, you could say that that's sort of the initial radiative imbalance that was introduced. So when we did this, we got about a 6.5 watts of radiative forcing instantaneously. And so we can compare these numbers across different models. And so here are the models that I work on, WACCM, the whole atmospheric community climate model. And you can see that those numbers are around 6, which kind of is pretty close to the mean of all CMIP5 models, and well within the standard deviation. So the model seems to be reasonable in terms of its response. We calculate a climate feedback, which is the parameter, which is the slope of this line. So that essentially says that as you put more energy into the system, it's going to warm up and so radiate more. So there's sort of negative feedback. And then you've got the 2 times CO2. So typically, 4 times CO2 is what we run in our experiments, but we divide that number by 2 to get a 2 times CO2 value. And that's so this would be what we get in terms of how we're characterizing our climate response. So this is all very good. You might have noticed there are a couple of lines on here, and that was motivated by this paper. So there was a study that showed that depending on whether or not you had chemistry in your model, you got a 20% difference in the climate response. And we thought, well, that's not what I'd done some previous experiments and hadn't seen anything like that. And so and this is the UKCA model, a paper by Novak et al., showing that actually when you put an interactive chemistry in the model, you got a decrease in your response to climate. So when you're thinking about maybe running for other planets or that sort of stuff, you may want to ask yourself, well, do I worry about the fact that the composition is changing as well? And so this paper said, well, actually, a lot of the AR4 models didn't have interactive chemistry. We're getting the wrong climate response because they didn't have interactive chemistry. So we went back and said, compared our runs with and without interactive chemistry. So SC Wacom is specified chemistry Wacom, where we specified the radioactive gases, and we saw practically no difference in our models between these two. So there's something going on between these models, just a cautionary word, and this is for a relatively small perturbation, that how your model is put together and how it responds and the tunings you may have done in terms of water vapor and those sort of things may actually give you very different climates. Okay, so right now we're moving on to CMIP6. And so that's now all models will be performing what we're calling the DEC, and that is this standard set of simulations, which includes a historical simulation and a 4 times CO2 experiment. Everyone will do that and do some climate historical runs, and then they will participate as much as they can in these what we call MIPS, which is model into comparison projects. And each one will have a purpose in terms of understanding different parts of the climate system, the carbon cycle. So there are some MIPS that are looking at the geoengineering, and some of the like AirChem MIP is looking at the chemistry response. So all of these MIPS kind of listed here, and then intended to ask different or answer different questions in the climate about the climate system. So this is a massive undertaking in terms of computation. I think I just ran the numbers last night, and I think in the next 2 years, we'll be spending 460 million CPU core hours to do our simulations, and this is just for the next 2 years. So that's 26,000 CPUs running 24/7 for the next 2 years. So this is if we had 100% throughput and 100% utilization, which we don't on a computer, that's 20% of our computing at NCAR is just going to be dedicated to this activity. Probably with uptime and getting things running could be 40% of our time. So, and that's not to think about the petabytes of data that will be generated from these runs. And storage is actually a bigger problem, I think, than CPUs going forward. So, just to talk a little bit about modeling at NCAR, we've gone from a model that looked like this in 1996 to one that now is trying to do most of these processes in terms of components of the Earth system, clouds, ozone, how solar variability affects the system, an upper atmosphere, land models, ocean circulations, deep ocean circulations, this sort of thing. So, for instance, we have to run our models for thousands of years to spin up the carbon-nitrogen cycle before we can then, and we typically do that with a simplified atmosphere, and then we can couple on the more complicated chemical and upper atmosphere models to that. So just to get a model spun up for pre-industrial conditions is actually a huge undertaking in terms of getting the CO2 fluxes right in the model. Okay, so how do we put these models together? We remember that I said that things haven't changed too much. So we have these, what we call a coupler, that couples different components and passes fluxes between the systems. And each one of these system components can actually be run as a data component or as an active component. So for instance, if we want to run with specified SSTs, we can read in and at sea ice, we can read in that from a file and just and know that the atmosphere is seeing the observed temperatures, and so we can test our model in terms of will it produce the current climate. And then each one of these can, so for the atmosphere where I work, we have several components. We have CAM, which is the community atmosphere model, WACM, the whole atmosphere community model, and WACM-X, which is one where we've extended up to do space weather applications. And in that, we have several options in terms of the dynamical cores. Typically, we run with a finite volume dynamical core, but we're moving over to the spectral element dynamical core in the next few years, perhaps with a core called MPAS. So that's how we put these things together. Here's just some examples of what we can get out of the WACM model. So when we add chemistry into the model, we then benchmark it against whether or not it does things like gets the ozone hole right. So we can nudge the model to observed mirror winds as well. So we can remove the the variability in the winds when we're comparing to observations, and then see how well we compare to the observations here. And then we let it free run, and we see how if it's very different than that. So that would indicate that our temperature biases are affecting our results. And in fact, they actually agree quite well. So we're very happy to see that. That took a lot of work, and because in order to get the ozone hole right, you need to get the polar temperatures right in the stratosphere to within a few degrees. So it's a very critical test of our model. So, and then of course we're showing here that it looks like we're going to be getting back to sort of 1980 levels in little after around 2060 in terms of the ozone hole recovery. And most of these models are benchmarked in things called like an intercomparison project run by SPARC called the Chemistry Climate Model Initiative, or intercomparison, I forget which now. And so here we have, so that's how we validate the chemistry. We put in an aerosol package into the model that does prognostic sulfate aerosols. And we have the various emissions, and you can see how these all add up to produce the emissions. So this was Pinatubo here, and this is the area density, which compares well to observations over that period. So we benchmark our aerosol optical depth against the satellite record as well. Okay, so those are the things. Now I talked about how I work a little bit on the upper atmosphere, and so we have various flavors with different tops, WACM and WACM-X, where we start to pull in the thermosphere as well. And that came out of a long history of model development at NCAR, based mostly with Ray Robel was the lead, in which we went from the TGCM to the TIGCM. This is a thermosphere, ionosphere, mesosphere, global circulation model. And from that model, actually, there were several spin-offs. Steve Booker did the Mars TGCM and the Venus TGCM in the 90s. Aaron Ridley created GITM, and I'll show a few slides of his model being taken to other planets later. And then we have WACM and WACM-X here. So I probably don't have, this is a list. I won't go through this about what you have to put into the model. Gravity waves are very important. And of course, you have all the processes in the aurora. What you're trying to do for this is to understand things like the Sun-Earth connection. And so we have energetic particles. We've heard about those earlier in this week, how they can make NOx, and that can destroy ozone. And so this is actually quite a complicated process, and we've actually been looking at this in a little more detail. So we put in this chemistry. This is the D region ionospheric chemistry, where we start worrying about cluster ions and how they make nitric acid in the atmosphere from energetic particles. So this was our standard model, these blue boxes, and then we added in the green boxes in our chemistry package. And when you do that, you get this whole soup of positive and negative ions. It turns out the electrons in the atmosphere are not the major negative charge carrier, and so you have to worry about these ions, and that the positive charge is carried by proton hydrates in the lower atmosphere, up to about the fifth proton hydrate here. It's dominant below about 25, 30 kilometers. And when you do that, you actually can then start to look at things like what happens in a proton event. So, and in particular, things like what happens when you have particles coming in from the Van Allen belts, and they will precipitate down into sort of the upper stratosphere, lower mesosphere. And what's important about putting in this chemistry is that you won't make nitric acid properly in the model without this chemistry. You need these pathways. And so when you put that in, you get a lot more nitric acid. This is a study we did that just came out in ACP, I think, showing that nitric acid production is enhanced when you have this D region code in your model. Okay, so that's the Wacom model with advanced chemistry. We also have this model that goes up to 145 kilometers. I validate that again. We're validating that against for things like the Halloween storm in 2003. And so this is the ionosphere in the model, and you can see the equatorial enhancements. You saw a snapshot of this, I think, in Judith's talk. This is the TEC she talked about, total electron content. And so what we can do is we can study how something like a flare might affect the atmosphere. And so we took around with and without a flare, and we looked at the electron density. And what you can see is that there's I think I'm slowing your computer down. The simulation would show that what you see is you'll see an enhancement in electron density around here, and then it will propagate upwards, following these, responding to the electromagnetic forces, and push the electrons up. So it's going to hit about now, I think. Come on, there we go. Oh yeah, it's slow. What you see is that you had an ionization down here, and then the forces push this up and out, and so you actually get a split. And what that means is the electrons last longer in the atmosphere because they're going up into being pushed into higher altitudes in the atmosphere where the recombination rate goes down. So that's sort of a fun thing. I'm sorry it took so long. So where are we going in the future? We're looking at new dicores, and one of the things that we have for that is and this is material given to me by Colin Zarzicki, sorry. And so this is. Okay, we're taking a spectral element grid, which is on a cube sphere, and this has a nice advantage. It doesn't have pole problem. You don't have convergence lines, and then we're adding in resolution in the Atlantic to look at this idea of tropical, whether or not we can get the generation of tropical cyclones. So this is a standard resolution model, and this model is two-way interactive. It has enhanced resolution in the Atlantic, tropical Atlantic. And so now you can see that between these two runs, that now we're starting to resolve tropical cyclones and the genesis of tropical cyclones here and how they can propagate up. So really nice two-way coupling in these models. And this has all kinds of applications for what high resolution can do in your model. I don't have time to show this, but this shows that you can actually get something realistic in terms of the initiation of this tracks and where the tropical cyclones start. Okay, one thing you can do is you can actually initialize the model to observe SSTs and let the model run in high res. And here's an initialized prediction of in a half-degree model running at a quarter degree in the refined area of Sandy. So this is actually just from initializing the model. Nice thing about this model like this is it's about 6 to 7 times cheaper, and on 800 cores you can get this sort of simulation, an 8D forecast in 1.5 hours of wall clock time. So, okay, so I did talk a little bit about the history of ionospheric models, and okay, I'm going. Oh God, I'm already seeing a red number down there. Okay, so this is Jared Bell sent me these figures. I think they're really interesting. You can take GITM, which is the model that has history back to the NCAR ionospheric model, and look at neutral ion coupling on Titan. So you'd say, well, this doesn't look very different until you look at the scale. And what you see is this is 7 times e to the minus 7, and that's e to the minus 9. So what's happening is that the ion transport upwards is radically changing the ionosphere. And so without having those electromagnetic forces, you may not be getting the right ionosphere in these in Titan here. So this is one of the dominant ions in Titan. So there's and it's even worse further down here where this is 2 e to the 7 to 4 e to the 8. So you can see there's a serious issue if you don't have transport. Wow. Okay. Tilt your head. This is Saturn, and you can see that they've now extended GITM to include Saturn. This is in prep model going up to 3,500 kilometers, and you can see the strong forcing from magnetospheric inputs in the model at the high latitudes. Okay, so I guess one thing that I do worry about when people say we're going to grab a model off the shelf from NCAR and run it for a different climate or a different planet is that what our models are highly tuned for the present day climate. So there's always a word of caution here in terms of what you may be doing in exploring those axes that we've heard about in terms of parameters like the radiance or distance to the sun, and whether or not that physically makes sense to push that model in that direction, considering the parameterizations that went into the model. And I do wonder, if you're going to really push this little thing out here, what's going to happen to your model? So we should be a little worried about, or at least. So one of the things I'm thinking is that it may be time to go back to some of the simpler models, and we actually have these now as off-the-shelf models at NCAR that are supported. Things like an aquaplanet model, Held Suarez case. These models are using these brand new spectral element dicores. They do scale up very well, but they may be a better starting place for when you're really pushing these models out to very, very different than a standard Earth climate. And so this is where I'm going, actually. I'm thinking about how we take these simpler models and change things. Okay, so I think concluding remarks are that I think wait, I skipped over one, I think. Sorry, I wanted to point this out. Where's I lost the slide. Okay, so future directions, I think I should talk about this, that we have these new dynamical cores, non-hydrostatic, equal area, deep atmosphere. So we're talking now about worrying about gravity dropping off, the fact that you now don't have, that as you go up in the atmosphere, you don't have the same area. So there, and you have to worry about mass and changing composition. Improving physics. So this is getting expensive, and there's a lot of talk about AI and machine learning in terms of cloud parameterizations, but I really think that that's real black boxes then. And for this community, that could be disastrous, I think, if you start taking AI modules trained on the Earth and putting them around other planets. Aerosols are a big problem, still the biggest uncertainty in climate response and how they interact with clouds. We're pushing this down now to weather and climate models, so subseasonal to seasonal prediction, and merging these models into one model. This was done in the Met Office, the unified model, and we're kind of going that way now. So, okay, so I'll just leave my conclusions here and take questions, I think.
So, for the ionospheric modeling, how does that impact the surface temperature of the planet? Like, I'm curious. Like, I understand intellectually it'd be nice to do like forecasts for aurora, but like, why does it matter to the IPCC, like in that context?
So, I don't think it matters for the IPCC. So this is more to go into this application of space weather, space climate. What it is nice, though, is that, for instance, we've done these simulations where we've looked at what the influence on the thermosphere is of increasing greenhouse gases. And they're really nice indications in the upper atmosphere of climate change. So we see satellite drag is actually going down quite quickly over the last 30 years. And that's because of the cooling of the planet and the whole atmosphere is sinking. That has huge implications for space debris. So how long a bit of space junk stays up there, and there's a chance it's going to take out $1 billion satellite. So those sort of things we're we're looking at more the influence of climate on the upper atmosphere
So we have time for one question. Let's go to the back.
So can you speak a bit more about the balance between increasing complexity and generalizability of the models, which I think is really important to people in this room? You know, as you go to better dynamics and better physics, a naive person would think you'd need to tune it less, but I suspect it might be the opposite. And what's going to happen?
Yeah, that's why I think we should pause and ask. I don't really understand. I think now even our climate models for present day are becoming so complicated that really people don't understand how they respond to forcing. It's almost like a dart throw in terms of parameter space. In fact, it may be that it's optimized through the Monte Carlo in terms of parameters to tune the system. So I think we have to be. I think you may have to limit how complex you want to go if you really want to understand the system.